Hello everyone. So we'll now look at what is the last part in writing a design. So in the last session we saw the compile command and its options. How do we the different compile strategies we could use top down or bottom up? How do we liquefy multiple instances and so on. So now synthesis is done. Now our job is to make sure that the results are in line with our expectations. We'll see how to report, how to check for some design problems. Although this step may not be the last one, it should be somewhere between. So there are two things to reporting and checking. First is to check whether the design is good for systems. It will come somewhere here. So just after reading the design, we should do some steps. We should do some reporting commands to make sure that design is good for synthesis. It does not have multiple drivers and any unconnected input and output are expected, and so on. Then after synthesis, we should again check the design for two things. We will do that in detail. We look at how to report area, how to report timing, how to report the complete summary of the design evaluation. So we'll see all those commands that doing that. We'll also see how to save the design database and what does this design database contain, and what are the different formats supported, and so on. So let's look at the flow, the analysis flow first. So before even going to the optimization, by optimization we mean before issuing the compile command, we should verify constraints and attributes. Constraints comprise of the clause definition, input delays, output delays. Attributes are the max transition, max cap, and so on. We should check design consistency. We will see what design consistency means. Then during optimization, design compiler will throw up some messages. It will iteratively tell us that what is the cost function of each of the steps it's doing. For example, if we do design rule optimization, it will do design optimization based on the timing, it will do design rule system, it will do some area optimization. So at each and every stage of those, it will tell us what is the cost function at which it's working. For example, if it's working in the area figure, so you will see the area figure reducing. Now that is a very good metric of how good are your constraints with respect to your design. We'll see that how to customize that and how to do a check on that. Then after optimization, we have to make sure that our timing and first of all the DRT constraints are met. If the DRT constraints are not met, then what? Then we have to verify timing. There is a design compiler user guide which has a lot of, so it lists down all the commands. It is not possible to cover all the commands for doing this course. So we focus on the more important one, the more famous commands that are more productive to use, more effective. And there are a lot of other commands which you can go through in the design compiler user guide, and you can help inside the people to know more about them. We will focus on which are the most useful commands. So first thing is we've already talked about the report list command. So we should use that report list command to make sure that the library we are using is good. It has, if you are planning to use the IIT model, does it have IIT model? If not, then what is your other source of IIT model, for example? Does it have max transition and max transition? So this is one way of doing that, but then there's one more good way, one more sophisticated way of doing it, is by using the compile extra with minus check only option. So the compile command will use a lot of attributes that are present in the library. Now what happens if it doesn't find some attributes? Does it make some assumptions? So it will make some assumptions and it will move ahead. So this command, compile extra minus check only option, it will report the potential problems that could cause compile ultra to either stop or to make some assumptions which might not be accurate. So this command is more useful for some advanced features of design compiler, like design compiler graphical or design compiler. There's a tool feature called design compiler Turbo, which reads in the flow plan information also. So it does taking some physical data. So this command is very useful for that. Somewhat less useful for the normal compilers that we do. So, but still, you could try and run that during one of the labs to see what it reports. So I'll just list down the most obvious thing that it reports. It will tell if there are any multiple logic libraries there with the same names. That means, let's say you have by mistake you loaded libraries from two different versions or two different standard cell libraries from different windows or whatever. And what is the name classes? That is, there are two versions of an and two cell, two input and gate. Let's say, what happens now? Design compiler, they are not unique. The design compiler would want to make sure that it's using the correct one. So you should point only the relevant. You should only point to the relevant kind of library in the link library in the target library. So it will report that if you have such kind of problems. It will report some discrepancies in technology data between multiple physical libraries. Don't worry about talking about physical libraries. Physical library means that it's related to the physical. So the physical library, apart from time and media, will also have the XML coordinates and so on. So it's not in the scope of this course. It will tell again. It will tell about don't the attributes of future hierarchical models or elements. Don't worry about this also. It will tell about floor planning information. There will be floor planning information. So again, most of the checks it will do are with respect to the physical data, the floor planning data, which will be used in DC Topo. But still, it will give some information about if there is some other attribute missing in the library. You could try running that on your example design. So the recommendation is to execute the compile ultra with the same set of options that were used when we used the check only command. So, for example, as I mentioned that you could use a basic to start synthesis. To do a trial synthesis, you could work on a synthesis without scan and without boundary optimization. The command would be compile ultra minus no boundary optimization, etc. So the same set of options you should use with check only. So that because the checks performed are with respect to those options, right? So just try doing that. I haven't myself tried a lot of. I remember only doing that only once. So I don't use it very often, but it's a good thing that we should start using it. Then now we talked about checking the design for problems even before going to compile. Check design is the command that will help us in doing that. It will do to check the consistency. Consistency means a lot of things. It's a combination of a lot of things. It means that there are no unintentionally unconnected codes. There could be intentionally unconnected codes, but then you should know. So it will give you a report, and duty of the designer to make sure that whatever it shows as unconnected input or output code are actually by design and not by mistake. No unintentionally tied code. So many times what designers will do, they will instantiate some codes and not use them for the first version of the synthesis. They will maybe use it in the other version, in the subsequent versions of design. So either they will leave it unconnected or they will tie it off to 0, so they will try 0 on the output or 1 on the output. So it gives you a report of those codes which are tied. No cells with input or output pins. Now this is more dangerous. Why have a cell for which the inputs and outputs are not used? It is not. It is highly. It is incorrect. In fact, let's say I am using a standard cell directly in my design. I am using an AND gate or an OR gate, and I leave one of the inputs unconnected. It's a problem. It's an error. In no scenario I should do that, because then design compiler will use some assumption to tie off this port. Either it will tie off this port or it will remove this gate. So for example, an AND gate, if the input is tied to 0, then the output is always 0, so the gate in fact is not required. You could drive the output net directly to 0 without instantiating the gate. So So design compiler might remove such cells if they are not don't touch. There is no don't touch on board. So it could create problems for the interface. So it will report such cells without an input or output. It will also tell if there is a mismatch between cell and structure. That means if there is a mismatch between a module and its instantiation. Right. So maybe you instantiated some module but forgot to connect some output pins. That kind of problem that you report. Or there is a 5-bit bus and you only connected 4 bits. So that's the problem that you report. Multiple driver nets, very important. Ideally, you should implement the multiple driven logic. You should not let DC in for it. You should design it. You should use the tri-state inverters or corresponding logic yourself correctly in the design. Ideally, you should not let DC in the multiple driven logic. Recursive hierarchy means that it's more related to the function of building recursive function, so it will tell you about that. So the best practice is to always ensure consistency before proceeding to synthesis. Although it is true that a good verification simulation environment will catch most of them, but many times synthesis is a very popular way to gauge performance of a design. So you will do synthesis a lot more time during a whole design cycle to gauge what is the performance of your design. So it's a very good practice to make sure that. So many times the RTL, the design itself is not final. It's in development phase and you are doing synthesis. It's a good practice to check consistency and feedback it to the designer. The problem. Then this was the check design was before going to compile stage. Now during the compile stage, DC will print compiled off, and what all information will it give you by default? Here's a list of that. It will tell you what is the elapsed time. So this is the leftmost column is the elapsed time. It tells you the time it takes during each of these steps. It tells you about the area. It tells you about the worst negative slack. The slack is the difference between, let's say, for a register to register path. We will come to it an example timing report. So if a signal is expected by some time, but if the signal arrives later, so the expectation is set according to a design rule. So the clock you define will tell DC that at this time the signal should arrive, right? Because the register to register path by default should complete the timing transaction should complete within one clock cycle. So this sets a restriction on the data arrival time. So data at the capture clock should arrive at some time. This goal time, the difference between this goal time and the actual arrival time is called slack. If it is negative, that means that path is not meeting timing. So this will tell you what is this column tells what is the worst negative slack of among all the critical paths. So it will also tell you about the total negative slack. Total negative slack is the sum of all the worst negative slacks of all the paths. It will tell you what is the design rule cost. Design rule cost, if it's positive, means there are some design rule violations, and it will tell what is the endpoint that has the worst negative slack. So it is configurable. There are additional fields. These are the fields, additional fields: match delay, memory, timing, leakage power, and so on. And this variable can be used to customize it. But the first step is you should be able to understand what does each of these fields means. And so, for example, in this log file, we see that as the time progresses, the worst negative slack in this step going from step 1 to step 2 comes down. So this is where the design compiler is optimizing the design for timing, for performance. The total negative slack also gets reduced, although the endpoint of the worst negative slack remains same. So it means that DC is optimizing for timing. You will see a lot of these logs during your labs, so please pay attention to those. If you find that it is taking a large amount of time in some of these steps, there is design rule, interesting design rule violation, or fixing timing, you should go back and check your constraints. So this log is a good indication of how good are your constraints and how realistic are your performance goals. So now this is a summary of all the commands that will help you gather more information. Now we are talking about the stage where compile is done, and now you want to report area, all figures. You want to get all the reports related to the design, the compile design or the map design. So this is a summary of commands. So please notice the left hand column which talks about the design object. We talked about what the objects are. The objects are design, instances, references, pins, ports, nets, blocks. These are all kind of design objects, and these are the commands that work on these design objects to give the description tells what it actually does. For example, let's talk about the design, the object design. So when you talk about design, we mean the current design, the scope of the current design. So report design, we'll see what report design does, what report area does. Report hierarchy, report resources. So all these 4 commands, they will report design characteristics. It will tell us what is the area and the object counts. We'll see example reports. Report hierarchy will tell what is the hierarchy, how many instances are there, and so on. Report resource is specific to the designware resources, the adders, multipliers, and so on. It will tell us these details. We talk about instances and references. There are commands, reports and report references. They display information about instances and references. Then we talk about pins. So the command report translated. Some of the commands work on multiple design objects. So report translated fan in and fan out work on either pins or ports or not. Please, if you do not understand the difference between pins and ports, please refer to the earlier slide. The ports only refer to the top level inputs and outputs. Pins are inputs and outputs of internal hierarchical design. Right? So these commands report the fan in and fan out of a respective port, pin or net. Report bus tells us about the bus ports. Report port command is very useful. It tells us about in summary about the input delay, output, any max capacitance, max transition, or max capacitance. Report port gives us a summary of the capacitance that you applied on outputs using set load. You might have applied any transition at the input using set input transition. It will tell all those information in one single report. The command is report port. Again, report net will tell us about the net characteristics. Similarly, report clock works on clocks that we declare. It gives us a summary of our clock. Let's see some reports. So report area. These are the important reports that you should use after the compile is done. The report area works on current design. It tells us. So this is telling us what is the design name. This tells us that this tells us that what are the libraries that are used. This tells us about the design object, number of ports. Please note that all this information is specific to current design. Number of ports, number of nets, number of cells, number of combination cells, number of sequential cells, number of macros. This means any. So we see that from the library report, we see that only some sort of standard cell library is being used. So the number of macros is 0. If you, let's say there was a memory here, the number of macros will reflect the number of instances of memory. It tells us what are the number of buffers and motors. Then it tells us this is the area detail. The combination area, non-combination area includes sequential cells plus memories if there is a case. If the wire load area has 0 net area, then the net interconnect area is undefined. Total cell area is the sum of combination and non-combination area. Total area is the sum of total cell area plus net interconnect area. Since net interconnect area is undefined, total area is also undefined. You might have the case In fact, I remember that in the lab, the net interconnect area is not 0. So the total area is the sum of cell area and net interconnect area. Now, in my opinion, net interconnect area is not a good figure to have. Since wire model is just an estimate, so the area of the net is also an estimate, and it's not a good estimate. The area, in fact, is not even close to the physical data. The wire model is very important from timing point of view, from gauging the performance, because you cannot ignore the timing of the net. But the area figure is more misleading. So it is a good thing nowadays. All wire models have 0 interconnect area. It doesn't mean the area is really 0. It means that the estimates are not good from area point of view. They are okay from timing point of view, but not from area point of view. Now let's say some other commands. The report design is one such command which gives us a good summary of the whole design. So it lists the operating condition. It tells us for example, the header. Again, it works on the current design. It tells us what is the design name. It tells us what is the version of design compiler being used. These are the libraries being used. It tells us what are the operating conditions. So this is the operating conditions WC form from this library. It tells us the process value, temperature, voltage, the interconnect tree, and so on. So wire model, it tells us that it is selected manually by the user. So this is the wire model. It tells us what are the input delays which we have specified, what are the output delays. We will talk about disabled timing arcs extensively in Unit 5. We will not. So Unit 5 we will discuss more about something called timing exception. So we will talk about disabled timing arcs while discussing those things. So these two commands, report area and report design, will tell you everything you need to know about the area. If you, let's say, your design is hierarchical in nature, which is in most of the cases, you could change the design by using the command current design, and you could report area as that particular hierarchy. If you want to know the total shift design, total area of the complete design, obviously you would work that the calculator. So you could change the current design and you could report this metrics, this data at any level of the design. Now let's look at the commands which will. So we saw how to report area. Now let's see how to report timing. Now again there are a lot of commands. Report design does give you some insight into timing by reporting the wire load model, by reporting the input data and so on. But the most famous command is this one, report timing and report constraint. Then there is a command called check timing. Now check design told us if your design is good from the connectivity point of view, from the consistency point of view. That is, if your input and output ports are unconnected, you have multiple drivers and so on. Check timing, on the other hand, works on the design constraint. It will tell you if you have some problems related to timing constraints. Report port we've talked about. I haven't used report timing requirements. So this is a more famous version of this command in time that I use most of the time. We'll come to that in Unit 5. Report clock will report the clock in the design. Then we'll see these three commands: report timing, report constraint, and report delay calculation. Some more detail. So this is the check timing. So check timing will give in design compiler. Check timing will tell you why I say design compiler, because same command works in prime time, but it gives much more data than design compilers. So many commands are common between design compiler and prime time, but some commands are very specific. Some commands will give you more data in design compiler if they are related to synthesis. But all the commands that are related to timing, such as check timing, report constraint, They, in most of the cases, they will produce more data than more data when it comes to prime time, because prime time is the static timing analysis tool. It's a tool that deals in timing. So everything timing wise, everything in prime time is superior to the things that help us deal with timing in design compiler. Design compiler is more of an optimization. It's not a timing analysis tool. Prime time is a timing analysis tool. So all commands related to timing analysis. This is analysis, right? We are talking about check timing, reporting timing. These are all analysis commands. All these analysis commands are much more powerful in prime time. So we'll see a lot of that in unit 5. So check timing inside design compiler tells us about unconstrained timing paths. So if we go back to basics and note down what are the timing paths. Timing paths are of 4 types: input to register, register to register, register to output, input to output, combination path. There are other type of groups also. Again, unit 5 will deal with them in more detail. But for design compiler purpose, for this purpose, there are 4 kind of timing paths. If any of the timing paths is unconstrained due to some reason, then design compiler will warn us about it. Now, what could be the reason? For example, you have an input at which you haven't applied any input delay. It means that from that input to the first clock that captures that input, the clock that captures this input, and the first clock that captures this input, that path is not constrained. There is no goal set. So DC will warn you about this. Will it stop doing synthesis? No, it will not stop. So this is what you do after synthesis. After the first pass synthesis, you analyze the report. What happens if it's unconstrained? DC will go ahead just fine, but that path will be slow. It will not make any effort to optimize timing. It will make an effort to optimize area. If the input is registered, that means there is no combination logic between input and stop. There is no area to optimize. Right? So it will tell you, what if your design has multiple clocks and you forgot some clock. If you forget any clock to define only one clock, the registers in that clock domain will be unconstrained. So it will tell you about that. Then it will tell you about the clock gating logic, that if any clock is gated by any input pin. That means clock gating logic refers to the gating of clock. So what you could have, you could be using an input and ANDing or ORing with an input clock. So it means you are gating the clock. So clock gating logic, you should be very careful about it. We'll see more of clock gating in power compiler when we talk about power, the dynamic power, and how clock gating can reduce dynamic power. We'll talk about that in next few sections. But you should review your clock gating logic in your design, because if you have it by mistake, then it can be dangerous thing to have. So it will give you warning about those. It will tell you whether your design contains unmapped cells. What is the case you might have an unmapped? Unmapped means that DC hasn't mapped from GTEC to. Now please remember, as soon as you do an elaborate, DC will create a GTEC netlist. It will map the design to GTEC. That's always the case. But it might find some logic where it is not able to map from GTEC to standard cell. And in that case, it will leave that logic in the form of GTEC. Do you want that? Obviously not. Ultimately, our aim is to get a netlist that contains only the mapped components. An example, let's say your standard cell library does not contain a flip-flop with async reset, and in your RTL you have inferred an async reset. Now, async reset is a logic that cannot be exercised by any combination logic. If the flop with async reset is not present in standard cell library, DC cannot do anything. So it will leave the flop as it is in GTEC format. So it will have a secgen instance corresponding to that order block with async reset, and it will leave it as it is. And the check timing command will tell you that the design contains unmatched service. So it's a very useful check. You should always do this check for unmapped logic and make sure that it's correct either your design or make sure you have a correct library. Now the command for report clock, it will tell you about all the clocks in your design. So this report shows that there are 3 clocks in the design. It tells you about the period, the waveform, the source means at which pin the clock is there, at which pin the clock is created. For example, this off-chip clock, it tells us the period, but the source is empty. Empty source means it's a virtual clock. We'll see later how virtual clocks are useful. Then for each of the non-virtual clocks, it will tell what is the rise delay, fall delay, if you have any latency defined. It tells us about the uncertainty. It tells us about the objects the clocks are reaching. So pi 2, for example, is reaching this FFN CP, and so on. So this FFN is a clock, CP is the pin of the clock and that. So report clock, you could simply do a report clock. It will just report till this part. If you say minus q and minus attribute, it will start giving you more data. Again, any command you could do a man or you could do a minus l to know more about the options. Then report QR. QR means quality of results. It gives the good overall status of design timing. It gives the timing summary for all path group. What is a path group? Path group is defined always by the capture clock. So a register for which, let's say, the capture clock is X, the path group by default is X. We could create different path groups by using a command called group path. We'll come to that later. But for now, you can understand that, for example, let's say there's an input register path. Now the path group for that would be the clock name of the clock that captures data on the clock. So here we see, for example, there are 2 groups, clock 1, clock 2. Now it tells us what is the levels of logic. Levels of logic means how many combination logic stages are there for the burst path. It tells us what is the critical path length. That means critical path length means that what is the maximum amount of time taken by a path in this clock group. The critical path that is violating, that has a slack of minus 2.64, the total amount of time that it takes for data to arrive is 3.64. It tells us what is the critical path clock period. So clock period is 11.32 for this clock 1. Total negative slack, that means it will sum up the burst negative slack for all the violation paths in this path group. That is a total negative slack. It tells us that total number of violating paths 59, total number of hold violations is 1. Similarly, it will give a summary for the clock 2. It will also give the hierarchical cell count and hierarchical port count. It will tell us what is the leaf cell count. I have already discussed what the leaf cell is. If you don't remember, please refer to the earlier to the last session. So report QR it tells us, it gives us a good overall status of the design time. Right? Now this is just a summary. What if now I know that okay, minus 2.64 is the worst negative slack in the clock group clock 1. Now how do I go into specific topics? I had the summary, but now I would want to know what paths are violating, why are they violating. This information, once you get this information, it will help you in fixing your design, right? So now a second level of summary is provided by report constraint. Report constraint, as the name suggests, tells you everything about constraints. What are the constraints? Constraints can be timing or design rules. Right? The report constraints has a lot of options, and as soon as you do report constraints without any options, it gives you the difference between user constraints and option design timing. So it tells us it has so many checks: max transition, max fan out, max delay, setup, critical range, min delay, leakage power, area, and so on. So it has so many checks, all the checks that your design has. If you design a clock, automatically max delay or setup check will be in place, min delay or hold check will be in place. The library has max transition and max capacitance and max fan out numbers. All these three mean that they are design constraints. So it will give you a summary of all the design constraints. If you say report constraints minus all is a short form for all violators, it will tell you all the violations that are in the design. Right? So, for example, this report constraint minus all violators. Now it is reporting for max delay or setup check for this clock 1 group. That means all the paths that are captured at clock 1. Now it starts giving us endpoints. These are should be the output ports. So it tells us that at these output ports, data 15, 13, 11, and 12, the required path delay is 1. Actual is 3.64, so the flag is minus 3.64, and the status is violated. What it means is that according to design constraints, the required path delay should be 1 nanosecond. This is the goal, but actually it is 3.4 nanoseconds. So you are violating by minus 2.64 nanoseconds. Right? So this report minus the option minus all violators will give you a list of all the violations. Right? Now it told us what is the endpoint. So report QR gave us a summary, how many paths violated. Report constraints minus all violators lists down each and every endpoint that violates. What about the start point? What if I want to see the complete path? So please remember, for example, a register to register path will have a start point register. It will have the combination logic in between. It will have the capture register. So I want to see all the details. So the command is report timing. Let's see the next slide. Report timing, one of the most famous commands. It gives us path timing report. Extremely flexible. It has a lot of options from to minus max paths, minus net, it should tell you minus condition, it will tell you capacitance, and so on. We'll see a lot more of it in the lab, but I'll just give a summary of it. So report timing report typically has the other options are other information in the header is very obvious, the design name, the guide and so on, operating anything. So it starts with a start point. So it has a start point, it has an end point. It tells us what is the path group. Path group will be usually the capture clock. In this case, it's none. So that means there is no clock that is capturing the group. We'll see. This is the example is of an unconstrained report. Unconstrained means there is no goal at the capture port. So either it's an output port, or it might be the case that it's a clock which does not have any clock. So in this case, it's an output port. So the start point is an input port, end point is an output port. There is an input delay, which is 0. So input is Cin, it goes to an AND cell. So Z is the output, it reports on the output. It goes through so many adders, instances, and carry out of those. The carry out is the pin. The cell is probably a full adder. The CO is the carry out pin. So this path goes from the input to output to a lot of cells, a lot of combination cells. It goes to Cout. Now Cout has no output delay defined. If there is no output delay defined, there will not be any path group assigned. So therefore the path group is none. Data arrives at 12.38. The left column, the INCR is the incremental delay for each. So this is the delay attributed to each cell. So for example, 2.27 is the delay of this full adder, and the path is the cumulative delay. So each of the cell delay is this. Total path delay is this. So the path delay is 12.38, and there is no output delay defined. There is no goal, so there is no concept of flag. any time if the delay is, we cannot judge if the delay is more or less because we don't have a goal set. This is a summary of the very basic. So this is only what we discussed here is just 1 or 2% of what report timing can do. Report timing can do much more. This is a command that I would recommend each and everybody to read the man page. You read the man page, you will have some information with you. Obviously, it will be difficult to grasp the complete information. But then when you start using it, you will start remembering what you read in the man page. Again, when we go to prime time, this command is much more powerful, and it has some more options, and it is the command that is used most extensively in static timing. It's a very important command. Please do read more about it. Please try and understand what it actually reports. Right, so the last command. So we have gone progressively from the summary part to reporting the endpoints which are violating, to using report timing to tell what the violation. So report constraints tells us that what endpoint is violating. Report timing further tells us that what is the start point that is causing the violation, and what is the delay of each and every cell in the path. Right? So we have gone from summary to more specific. Now let's say this, for example, this full adder is taking 2.27 nanoseconds, but the other full adders that are following it, each of them is taking just 1.17. So there is a difference, a big difference in the delay between this full adder and the rest of the full adders that form. Now, as an engineer, I want to know that what is causing it. What is the calculation that is involved here? How is DC calculating the delay of 2.27? I can use a command called report delay calculation. I can say that. So here the example is like this, right? So add 8 U11. Now I say report delay calculation. I ask DC, how did you calculate delay from input of this cell? So the cell is same, add 8 U11 from the input A to this cell CO pin. Now DC will tell me that from this pin, input pin to this output pin, the input net transition time is this. The inference it will tell you the calculation, the formula it used to calculate the timing, and it also depends on the library. So if your library is non-linear delay model, the calculation would be different. Please remember we have very good slides in the library session that we discussed. It discussed the non-linear delay model. It also discussed the linear model. So from this calculation, I can say this is the linear model because it is talking about intrinsic rise time and rise resistance. If you remember, non-linear delay model is a lookup table based model. So this calculation, it tells us that how did it compute the rise delay of the output, how did it compute the fall delay. So it is telling us that for rise delay, it used the rise intrinsic 1.8 times plus rise slope into dt rise into some factor. It calculates the rise resistance, so it will give you all the calculation. So it helps us to know. However, you will not do it for a lot of cells. You will do it for only few cells for which you want to understand. First of all, in any decent design, in a big enough design, there are thousands and thousands of timing paths. Will you look at all? No. You only look at the ones that matter. What matters? The critical path that are followed. Now, in that critical path, do you look at the delay calculation for each and every cell? No. You look at the timing, report timing. You figure out what are the cells which have worse delays, and most probably you will know the reason. If you have some experience, you will know that either it has a bad transition or it is driving a lot of cells and has a bad capacitance with the output, and so also the reasons are few and common, but report delay calculation will help you in debugging more of that. So you can again try this command in the lab. The report delay calculation in the lab will not match this the one in the slide because the labs will have non-linear delay model. This example is from the linear delay model. So just see if you understand the delay calculation of one cell in one time report. Now this slide will tell us that, let's say now I am doing a performance evaluation on my design. I do not know beforehand that what clock frequency can I operate on. So one of the useful thing is, what you could do is, now let's say each technology has some data available on what is the percentage of cell delay versus net delay. For example, in 90 nanometer, if I remember correctly, the percentage of cell delay to net delay for the statistics is collected over a lot of designs across the industry. So in 90 nanometer, probably the cell delays were more like 70% of the design, and net delays were probably 30%. As we shrink, the cells are becoming, the technology is shrinking, transistors are getting thinner and thinner, cell delays are improving, but interconnect delays are not improving. As a result, in technologies like 45 nanometer, I guess the cell delays would be 50%, net delays would be 50%. Now, what I can do is, I can set a variable called set 0 interconnect delay to be true, set 0 interconnect delay not to be true. I do a report queue. What DC will do, it will make all the interconnect delay 0, and it will report timing based on only the cell delay. Now let's say if in 45 nanometer I know that the ballpark figure is 50%. If I know only the cell delay, and so I can judge what is the clock frequency I can operate on. So this method, setting the 0 interconnect delay to be 0, it helps us in assessing the designing constraint frequency. Please note, we are talking about the map design. Map design means after at least one pass of synthesis is done. So this is the flow. You do compile first, you set this variable to true and report to 0, and again set this variable to false. So this is just a reporting command. So this, if you want to do any more compilation steps here, you have to set this to false first. Just remember that. Try it out in a lab. You will find this is a good way to see that what is my cell delay part and what is my wire load model or interconnect delay part, right? To separate them out. So you could find that, okay, yeah, my design with the 0 interconnect delay, it works at 200 megahertz, but when I switch on the wire load model, it works at 300 megahertz. So it will give you some figures with respect to what frequency is important. There are two attributes I want to talk about. One is the don't touch, other is size only. So what would happen? Let's say I have instantiated a cell in my design, a very specific cell, or let's say I have instantiated a few buffers in my design, and I do not want design compiler to optimize them. I can set a cell design compiler and set don't touch on these cells. So design compiler will not optimize them, right? So many times you get a design from some third party, you get constraints or from third party, and you find that some of these cells are not getting optimized. It might be due to a don't touch attribute. The don't touch might be set in the design constraint. How do you debug? So first of all, if DC does not optimize the remove a cell or a net, it is often due to a don't touch. Explicit don't touch is straightforward to debug. You can grep for don't touch in a design constraint file. You can also report don't touch by saying using a command called report don't touch command. So it's so you should know that there is such a thing called don't touch, and it is mostly used to make sure that some of the cells or some of the nets that you don't want optimized off for some reason or the other, and how to debug this. Right? So this is the command is called report don't touch. Again, there is a second attribute called size only. Now let's say I instantiate a buffer, and I want that, okay, fine, the buffer should not be removed, but I tell DC that yes, do not remove it, but you may upsize it or downsize it, maybe to solve the design rule problem. So let's say if I have a buffer and I know that it might have a large format. after being mapped. Let's say it's driving a large fan out, but I do not know for sure that what is the drive needed on it. I'm not too sure about that. So I can choose a lower drive in my instantiation and tell DC that it's a size only attribute. Set a size only only by using a command set size only. Now DC what it will do is it will keep the buffer, but it can upsize it to solve design rules. Right? So size only tells DC that this is not to be removed, but its drive can be changed. So for reporting such instances, you can use report size only command. It will tell you if you have any size only attributes there. So you can read more about it by doing the math. So this was all about analyzing reports. So we saw. So this is the let's go back to summary. So this is the list of commands that you could use to report on design objects, to report on area. Again, this is a list of commands you could use to report on timing, on design timing. So there are two reports, area reports and timing reports. So I listed down the more famous commands here. Then let's look at, now you synthesize design, you have analyzed the reports, you analyze timing, everything is fine. What's the next step? Next step is you have to write out the design database, and in the chip design flow, digital design flow, the backend will now take over. Now this design should be laid out, placed and routed, and then it will go to fabrication if you're working on a real chip, right? So the next step is to write out the design data, and what are the formats available to us? There's a format called DDC. It's a Synopsys internal database format. Verilog. These are the two most important formats we will work on. You could read about this. There's VSJ also, increasingly going out of use. There's a Milky Way. Milky Way is again specific to Synopsys backend tools. So most popular are DDC and Verilog. Different. DDC can only be read by Synopsys tools, and DDC contains netlist plus constraints. So if you say write minus format DDC, it will write out even the constraints form. And so for example, we've seen the lab, I'll write out a DDC, I'll read back a DDC, and we will see that all the constraints are written. It will have the, so when I apply clocks, when I apply input delays, output delays, all this information will be written out in DDC. Verilog is a plain netlist. It doesn't contain constraints. So what's the use? Now let's say the backend person is working on Synopsys tool, so I can directly give DDC, right? Because that's it. I don't need any other file. But if the backend person is working on a backend tool from some other company, let's say from Cadence or Mentor, now those tools will not read DDC. They need to be given Verilog. So I need to write out a Verilog, plus I need to write out the constraints separately. So there are different formats for constraints to use in data. Now I need to give the Verilog plus the constraints, both of them, to the backend tool. Right? This is the write command. You could choose the format to be DDC or Verilog. Minus hierarchy. Without this, design compiler will only write out the current design, not the complete hierarchical design. So you should always use minus hierarchy. Minus output tells what is the name. If you do not use the minus output option, by default it will write out the top design. Okay. Now, when we write out Verilog for the backend engineer, and if he is using, let's say he might be using any tool for doing backend, there might be issues in the naming convention. So before writing a netlist within DC shell, we have to make sure that all net and port names conform to some naming convention that is used by the layout tool. Usually, in most of the cases, every tool will recognize Verilog. That means it is safe to give a Verilog netlist to the backend tool, but we have to make sure that the Verilog netlist conforms to the Verilog naming rule. Now the design inside design compiler, when the design compiler is working on the design, it will not follow the complete Verilog, the whole Verilog naming convention rule, right? So we have to make sure that before writing out, we should tell DC that you should make sure that the names are corresponding to regular. How do we do that? First step, no change, we read in the RTL. Second step, no change, we compile the design. Now before writing out, there is one more step. We use the command change names. For example, we can use something like change names minus use Verilog command whenever we want to write a Verilog BSP design. So we issue this command change names minus use Verilog hierarchy names is applied to the complete design, hierarchical design, and then use the write file command minus command Verilog. Right? So it will also list when we issue change names command, it will tell us what all names it is changing. So what I would tell you, I would recommend in your lab, write out a netlist without using change names, and then again write out a netlist with change names. See the difference. I'll probably include this in my lab. We'll write out both the netlist before change names and after change names and see what is the difference. That will give you some idea into what kind of name change occurs. Right? And then we can use change names and use again the command write file minus command Verilog, and then deliver this netlist and plus constraints to the backend engine. Right? These are some of the additional commands. Some of these we have discussed. Some of these we'll see in the labs. And for more information, you can go to this design compiler user guide, which has a list of all the commands. You already know how to use the design compiler. Thank you.